Wonderful. So we had engaged with this prompt here to kind of say, okay, what would it be like to be a microorganism dwelling in this very rich regenerative soil that we see in this image? Even though it is a farm producing food and ag for a specific purpose rather than a natural setting, you can see that it's still regenerative in many ways, right? So you have plants, you have animals, you have some natural systems both above ground and underground. And imagining yourself as a tiny microorganism in this system is very similar to imagining yourself as a human being on a global scale, right? Because we exist within these ecosystems that oftentimes through human engineering can either be regenerative or can be depleted in various ways. So that first kind of double-sided image being an example. Okay, this one here. So just, I want to make sure that you can still see the slides. Just a quick thumbs up because I had moved things around. Okay, wonderful. Um, okay, so in our readings and resources for this week, we talked about ecological principles. And there was a lot in those resources, and there's a lot to be said today. So I'm going to kind of move through a discussion of some of the resources that we saw, but also I'm going to add to it today by talking about global biogeochemical cycles, some of which we'll focus on. So last week we had talked about thinking about environmental, social, and economic systems within a systems framework. And we had talked about settling that systems framework in nature. And so you guys had just some really amazing reflections in your sitting in nature homework, where you were sitting in various types of nature, right? Some urban, some very rural. Some of you went a far distance into kind of rural settings or natural settings for this assignment. Some of you were sitting in your own homes looking out of open windows, right? So lots of different ways of engaging within these systems and cycles. And I really appreciated all of those really rich reflections. And hopefully that's a seed for us to continue to think of ourselves within natural systems, both systems that include humans and various biogeochemical cycles around us. And we're going to dissect that a little bit more today. Um, some of the readings that we talked about reminded us of kind of the evolutionary timelines that we are kind of situated within. Specifically, when we had some readings around the Anthropocene, which may more effectively be called the Capitalocene. There's an article here that talks about that. There is a book that I think I have behind me called The History of the World in Seven Cheap Things, written by Raj Patel. Raj Patel has a number of great books on sustainability topics. But thinking about that concept, even either as a human focused or a capitalist focused kind of timeline within the historical timelines. But in the grand scheme of things, humans have only been here for a minute, right? So if we look at geological timelines and we look over history, we might also think about this class from the framework of how will we be remembered over evolutionary or ecological or geological time, right? As individuals and also as group, like human beings as a society. And kind of thinking about how we can implement various impacts and pressures to make that more of a positive memory or a positive footprint versus a negative one. Okay. And there's a discussion about plastics that was had a little bit in this week's readings, but also will come up later. Chicken bones, different types of chemicals, all of these things will probably show up very clearly in what will just be a thin slice of our geological history millions and millions of years from now, right? And so thinking about that impact is kind of an interesting framework. And a lot of what we'll talk about today is slow versus fast, right? evolutionary time versus human time, evolutionary natural ecosystems and their needs versus human needs and human impulse, right? And so having that perspective in mind is really important when we're talking about natural systems because we really can't define things like renewable resources without a time frame aspect. We really can't talk about sustainability without a time frame aspect. And so considering that is really important when we're having these types of discussions. So more soon on food, more soon on plastics and various types of waste and consumerism, but just kind of a way of putting these conversations into perspective. Um, Also, what one of the things that we're really trying to do, one of our action items for this term, is that eventually you have a project that allows you to identify your own principles of sustainability. And so we'll try to continue to think about principles of sustainability, ecological principles, principles of impact throughout the course. And so in your inner reading, there was one section that kind of dissected out some clear principles, some clear kind of standards that come up when you're looking at ecological systems, right? So, for example, matter cycles continuously through various webs. Most of the energy that drives ecological systems comes from the sun, although that's not always the case. Deep sea vents and some other ecological systems have a different basis of energy. Diversity assures resilience. Okay, so the more different types of species that you have in an ocean or in a droplet of soil or on the earth, or more different types of cultures you have within human societies, the more skill sets that you have to wade out whatever it is. It might be a pandemic, or it might be a change in the climate, or it might be whatever it is, a political change. So, the more skill sets that you have available, the more tools that you have to withstand that. And the fewer, again, the fewer you do. One species waste tends to be another species food. This is really important, especially when we talk about production cycles and food, which we will come back to. We'll mention today. It'll come up throughout the term. But whenever you separate production from waste, then you end up with pollution within ecological systems. But natural systems do not separate production from waste, right? In natural systems, something grows on the nutrients within that ecosystem and then dies and decomposes back into the nutrients within that same ecosystem or within a similar related ecosystem. And so these feedback loops are really important, and keeping them intact when we're engineering biological systems is really important too. Life does not take over and by combating, but by networking, right? So when you see this image of more of a healthy ecosystem that we had looked at up here, you're looking at just this immense networks, like even literally just physically networking. And we're going to look at roots again, and some of the networks and roots in today's lecture, but also just across different species and different interactions with the biotic and abiotic aspects of the ecosystem. And so when we were sitting in nature, we had looked at biotic and abiotic features. We had looked at where energy sources were, where food is, things like that. So these networks between biotic and abiotic features and between diversity within those features is really essential to sustainability of ecological systems or of any system, and also for resilience. Okay, I'm just going to take us back to the slide we were on. Here we go. And so really thinking about networking of diversity is really important. And so, of course, there are many other ecological principles, but these are a couple of standards that help us start to kind of have these discussions and think about these ecological systems and how they function. Okay? And when we think about our ecological footprint, it's really important to think beyond just our direct impact. So it's not just the number of liters I drink in a day of water or I use to take a shower, but it's beyond that, or even used sometimes we forget, like using to flush the toilet or wash dishes. Or there was a fun article we used to dissect in one of my classes that just dissected how much water we need to drink tea and coffee all the time. Like we always drinking tea and coffee. And it was just a fun article to think beyond those very direct things that come to mind when we think about our ecological footprint or the use of various types of resources. And so thinking also of all of the different inputs that had to come into play, all the different people that had to touch those specific resources that we then use, right? And in aggregate, that is our footprint. It's not just the immediate, like how many, liters of water did I drink or use to shower with, for example. And so that discussion is not meant to make us feel guilty. Although some of the resources in this class will push that lever a little bit. And it's not really intentionally to make us feel guilty, but sometimes with a level of awareness and the motivation for action, sometimes there is a point where we start to have a little bit of guilt. And I want to really encourage you not to sit in that guilt too much. Utilize it as a motivator for action. Utilize it as a motivator for knowledge. Utilize it as a motivator to find community. Um, you know, and sometimes give yourself some grace because sometimes you'll feel guilt because you feel like you're breaking some of the principles that you set up for your own self. And that's okay because we can never be perfect in all of these principles, especially when there's larger systems at play that we still need to slowly, and again, slow versus fast, that's going to be like our theme today, slowly kind of chip away at and make changes within. Okay. And so that's a really important kind of just overview, not just for today's lecture, but throughout the term. Okay. Um, so this diagram, I want to have like a little conversation around it. Another thing about the resources for this class, beyond just guilt, is that they will never be perfect in another way. And that is the equity perspective, right? A lot of times in the sustainability space, we will have discussions about limiting population growth, or limiting meat consumption, or limiting this or that. And a lot of those discussions fall more heavily on the folks that are impacted but not benefiting from the current state of material utilization and extraction, right? So folks that are impacted in various areas of the world by exploitation, by loss of land, by extraction of resources, by exploitation of labor, tend to maybe be the ones that have higher fertility rates, or maybe be the ones that are moving into a transition where they are having a better standard of life and eating more meat, for example. And I would say across the board, the resources in this week, particularly, but oftentimes throughout the term, just did not do justice to that equity piece. And so there's something that we'll look at as we move through the term called a just transition, which is absolutely essential to all conversations around sustainability. It's a transition that imagines moving to a more sustainable global system without the most at-risk communities carrying the burden of that transition, which they have already carried the burden of the impact, right? And for folks that have been historically privileged to carry more of the burden of change and personal impact. And that just transition idea is not well kind of woven through all of the resources at this point in the sustainability discussion, but it is coming up more and more, and it is becoming more and more clear throughout sustainability discussions worldwide. And so I really want us to be thoughtful of that, because it is essential to the discussions that we have. A lot of the impact of the most privileged lifestyles falls on folks that carry the impact then of climate change transition. And that can't be the case. So we had this discussion about population, affluence, and technology, and just thinking about kind of the footprint of individuals within what has been called, I don't, there's never like a good term when you call like developed and developing. Those are really like laden terms with a lot of isms across the board. But when you think of folks that have been historically privileged in various settings and folks that haven't, you can just see that the impact of what an individual in terms of resources that they will use and impact that they will have is much different. And this diagram would look very similar, or actually would look exactly opposite if you looked at how the negative environmental impacts of things like pollution, water scarcity, so on and so forth would fall on these folks. It would be exactly the opposite, right? Um, and so really starting off any and all sustainability conversations with this just transition framework is really important. And I just want to be honest that this week's resources did not do the best job at that. Some of the readings in the textbook continuously used like an I and we that was a very privileged I and we without really thinking about global communities. And then also some of the imagery in some of the documentaries that you watched were like very accusatory of certain cultures and their cultural like foodways. For example, without really thinking about broader impacts of consumerism and the fact that there's not really a market for the whole shark, for example. And therefore, only the fins will be harvested. So I just want to be really thoughtful about that specific conversation as we move forward in today's discussion. I also, as we're moving through, want to pause and see if there are questions or comments so far. Okay. Feel free to jump in if you have any questions or comments. Yvette, I see your mic turning on. Go ahead.
I actually do. I just got here, so like I don't mean to interrupt, but since you gave like an option to ask,
Yeah,
like what,
please go ahead.
oh, I was just saying like I just wanted to see what we were like talking about right now. You don't have to like re-say everything, but I just
Yeah, we're talking about, we're prefacing ecological systems and saying that it's related to our discussion that we had last week of settling ourselves within systems, but also moving forward, we're going to talk about biogeochemical processes that impact, humans, um, natural systems, social systems, economic systems, so on and so forth. Before we make that transition, we're taking a break to kind of make this note about just transition, always thinking about how ecological impacts fall and hoping that as we make a transition to a more sustainable world, that falls in a just way, which it hasn't historically. And so we're moving through the lecture presentation for now, and then in a little while, we'll start our discussion of those resources. Yeah, yeah, you're welcome. No worries. Other questions? Okay, wonderful. Feel free to jump in anytime, and I'll try to make sure to give us space as well. Um, Humans really do make like this special type of engineering on Earth compared to other species. So even though we are just one species within the animal kingdom, we have a really unique way of engineering the resources around us. And so as we move through our discussions today, we're going to talk about both positive and negative kind of impacts of our engineering. And I think there was this quote in our reading that says we are victims of our own successes sometimes. So, a lot of what we see as improvement in human standards of life or human access to various resources come with some sort of pitfall later on. And this goes back to that perspective. If we have long-term perspective when we're utilizing resources, it gives a different outcome than if we have a short-term perspective. And so, this is just a thought here. Another thing about human impact, is that oftentimes when we push various variables, we do them without understanding the full entire context. And that's not really a lacking in of our wanting to understand, but it is kind of an appreciation of the complexity of ecosystems. So just in 1 teaspoon of soil, you might have, billions, millions of different types of organisms that are interacting in that soil. And then in a square meter, if you expand, you're looking at just so many different organisms that are engaging with the abiotic environment or abiotic components of that environment to also engineer and build and create and deconstruct and decompose, right? And so if when we're pushing these various variables for our own benefit or exploitation, oftentimes we just miss so many different networks that are also going to be impacted. And that also came up in our readings that you just can't do one thing. You end up making an impact beyond that one variable. Um, it's not the most perfect or accurate image, but I love this image right here. It just reminds me of like what we call a hydra or a migration back to the soil. And I think that is just the basis of a migration to anything that is, beautiful and full and ecological starts with the soil, right? And so I just love this coming back to the earth, coming back to the land, coming back to the soil, and all of these different organisms represented, not exactly to scale. Like I think this is a bacterium and it's too large. But I do love this imagery, and it gives us some perspective, some positive perspective moving forward. Okay. And it also gives us a starting point. So I think really starting this discussion with soil is essential and important. So we're going to talk about what is soil, what is a critical zone, what are some nutrient cycles that feed into soil and ecosystems, and how do humans manipulate them? Okay, so I'm going to start with this, what is soil? And let me just give me a minute to activate the correct question here. Okay, so that question should now be active and you can engage. And this is a word cloud, so try to submit single words, but you're welcome to submit as many as you'd like.
Are you sharing the link in the chat or is it on Doodle?
I will send it in the chat. Yes, absolutely. Thank you for that.
Thank you.
There you go. Okay, I love that this says nutrient earth organisms, right? And then so many other just really great imagery coming out here. Microorganisms, rot, recycling, decomposition, materials, ecosystem, planet, compost, organic matter. So really, right, this discussion between soil versus dirt, right? this context of like dirt or dirty, but really soil is nothing like that. Soil is this aggregate of earth, minerals, organisms. It's a home for many different things, and it's the interface between air, water, soil, and living things. Right? It's the interface and it's the cyclical interface between those things. Thank you so much for engaging in that. I really appreciate it. Here's just another image that gives us a perspective on that interface between air, soil, living organisms, and then there's also a significant amount of water and moisture within this imagery as well. And so, soil being that interface is really, really essential that that soil is healthy, right? And so, we read an article about the Dust Bowl. Oftentimes, we think about the Great Depression as like this historical event, but not always is it tied to ecological principles, right? But really, the Dust Bowl at its basis has two components. It has the ecological disaster and the economic disaster happening around the same time at the end of the 1920s, right? And the ecological disaster is that we came in as colonizers of this land, and we saw that there's just this amazing fertility in that Midwestern area of the United States. Well, why is that? Why is that ecosystem, which can be called a grassland or kind of a grassland ecosystem or a prairie ecosystem, why is it so rich? It's rich because of the diversity of organisms that sit on it. Many different types of grasses and low shrubbery that are maintained by the cyclical processes of the larger grazing animals that are maintained by the few top predators that are in that area. And that cycling of those grazing animals in and out of those areas and their manure, right? One organism's waste is another organism's treasure, is an important system for maintaining that health of that ecosystem. So, as colonizers and folks that are now moving into more large scale monoculturing of food, we come in and we start to separate out those cycles one by one, right? When you remove bison and buffalo from the plains, right? Literally almost just decimating those populations. When you remove top predators from the plains, when you start maintaining your own monoculture rather than a variety of grasses or rather than a variety of plant life. And yes, you're monopolizing that soil, but therefore it will not be regenerative. It will not be renewable because you've removed the systems that make it renewable, right? And it didn't take very long, right? It didn't take very long, within less than a couple hundred years, that topsoil essentially was so depleted, depleted of nutrients, depleted of life, and depleted of water. That's what dust is. Dust is just, the rock, small pieces of rock or material without any water. And then it literally can just blow away, right? And so it's not a natural disaster that happened because of a drought at the end of the 1920s, as sometimes it's made to sound like. It's a natural disaster that happened over a series of decades as we moved into those areas and separated out the parts of that natural system that gave us the rich soil that's there. It's the same thing that we're doing with rainforests currently, right? You're seeing the decimation of rainforest, like swaths of rainforest the size of, small countries being lost per minute, right? Predominantly for the production of cheap beef, right? Now, there are other reasons, like palm plantations are a big reason for deforestation. That's a little bit new because now we use palm oil as a cheaper alternative to corn oil, which is what we had used massively before that, right? So there are multiple different reasons for this, but a lot of it has to do with the production of cheap food, particularly beef. Um, rainforests are another example of ecosystems that don't on their own have rich soil systems, right? All of that biomass that you see in a rainforest is built on cycles. For you to have that very rich humus that you get in a rainforest, you'll have to have constant influx of leaves and dying animals and matter from the canopy. itself. You also have to have the influx of the rain from the rainforest comes partially from the trees. The evaporation of water from the trees is what actually makes the clouds above the rainforest. Without the trees, you lose the clouds that are the rain part of the rainforest. And so it's a very similar process. And what the end of which, what we saw in the Dust Bowl and what we see in rainforests is a process called desertification, which those ecosystems either temporarily or chronically, I don't want to say permanently, but chronically becoming deserts. Um, and that happens in just a couple of decades in the rainforest. So 10 years, 30 to 30 years, something like that, you can have a piece of land become a desert because it just doesn't have the input of organic matter that it had, especially with the compaction from grazing animals. And then a new plot of the rainforest has to be destroyed to then allow for that, economic resource. This comes back to justice too, because a lot of times we'll point to countries that have rainforests and say, why aren't so and so saving the rainforest? Why aren't so and so saving the rainforest? But the predominant benefactors of the destruction of the rainforest are us in privileged countries and our, exploitation of resources. And so really it's the case of the one finger pointing away from you and four fingers pointing back at you. Kind of situation. And we really want to be honest and thoughtful about that. Okay. So let's continue to talk about soils and what they hold within them. Okay. So first you might want to consider how soil is actually formed. And if you've taken other biological sciences or ecological science classes, you've probably seen this image of succession and different types of succession. But it's a useful kind of framework to work with when we're thinking about biological systems and soil. Oftentimes, soil is a mix of organic matter, which we call humus, and small rock particles, which we call silt, right? And that combination in different variations gives you soil that is more clay-like, more loam-like, or more silt-like. Maybe if you're a gardener, you're familiar with some of those terms, right? But if we look at over time, how did we get that mixture? Oftentimes, you start off with ecosystems historically, or through some sort of disaster or event, like a volcano, that were mostly bare rock. And then you have what are called pioneer species. I think I have an image later in the presentation. Let me just pull that up. Oh, not that, sorry. Pioneer species are organisms that are basically able to utilize nutrients out of almost nothing, like bare rock, right? And those tend to be your mosses and lichen. And it's interesting. So this image here I took on my walk one time. This is this constant tug and pull between human engineering and nature, right? So we've taken it down to almost bare rock here, but then there's moss and lichen that can come in and use those little tiny bits of nutrients that are coming out of the little particles of that cement, and they can start to develop soil in those little cracks. What happens is the little particles of the cement and the moss, as they die, they build up soil, right? And so it is those pioneer species that come in, however it was, whether it's a human impact like these, or if it's a natural impact like these, that then build up those soil systems. And so oftentimes what we think of as weedy species, they're the ones that come in next, because these are organisms. Let me just take us back to the slide we were on. These are organisms, they're weedy because by nature they're opportunistic. They're able to jump in and utilize whatever nutrients are available to them, even if it's not abundant. And so those weedy, what we feel like are annoying, potentially annoying invasive species that keep coming back in, those are healthy organisms, oftentimes, unless they're invasive in their environment, that are coming in and helping to develop those root systems and break down more of the underlying bedrock. And as they die, contribute more to the nutrient cycles that are under those systems. And if that community is allowed to grow and sustain itself, it'll eventually get to a very diverse, what's called climax community, where you don't have as many of those weedy species because they need the sunlight, right? They're kind of shaded out, but you do have a diversity of tall standing trees and underbrush and all of the organisms that live in them, like with the rainforest. Now, some ecosystems will take you to this big, very large climax forest community. Some are more limited, like a desert, you just don't have the nutrients, the water that you need for a very large climax community. Something like a tundra, that underlying ice, you can't have large standing trees. And so, depending on the abiotic factors, the non-living factors, this succession here will happen differently. Okay. Um, and we had talked last week about the role of human actors within this cycle as well. And so native sciences know and have understood this process of succession and are able to prod it along or improve its productivity in terms of, human benefit using things like fire, for example, right? And so the fire is taking out some of those low weedy grasses, some of that shrubbery. The fire itself puts some of the carbon back into the soil and allows for some of those climax communities to develop. And so we have seen that in our previous discussion. Okay. Um, and thinking about soil as soil rather than dirt being really, really essential. And if we consider all those components that we've talked about and that dynamic nature of soil building up over, historical time, we can think then about the ecosystem services that it provides. And I know ecosystem services is an interesting concept because essentially what that is how does this part of our ecosystem benefit humans? And it is a little bit extractive, but it is an important concept to consider in environmental sciences because as humans we do a lot of engineering, and so if we can do that in a positive way, then we can really see beneficial impacts and outcomes. So ecosystem services of soil include nutrients for plants, direct and indirect health benefits for various species within the ecosystem, mitigation of erosion, groundwater filtration, gas exchange, and carbon sequestration, and various types of recycling, right? And so, like a lot of times, discussions around swamps, right? Swamps tend to be these ecosystems where you have a lot of soil and water filtration and things like that, but you also have what can be considered lots of bacteria and things like that. And so sometimes folks will want to remove in their engineering swamps, but now we're moving towards including swamp-like features like bioswales in our urban systems because we've realized that the filtration and the benefits of that soil and that filtration of the soil and the benefits of the soil are essential to ecosystems. Okay. And so this question of the word renewable, right? Renewable is an interesting concept, and it's a concept that we like to talk about. We want to use more renewable resources. But what is renewable and how is renewable defined? So soil is renewable, but not if it's exploited. Soil is renewable over hundreds of years, but maybe not over tens of years. And so anytime you're presented with the concept of renewable, in this case, we're talking about soil and nutrients cycled through, but any renewable resource, be thoughtful of that those questions that you might ask: when, how, over what period of time, so on and so forth. Okay. And that is essentially what we saw in this week's resource when we were looking at the ancient forest management through native peoples, in Michigan. So we're not going to watch that now, but you were able to see that in your resources for this week, leading up to this week. Um, so as a way of really putting this into context, yeah, I really appreciated it. And that satellite imagery that kind of gave us perspective was really cool too. Really thinking about scale can be so helpful. So I want to continue this discussion with some specific examples. And the examples I want to use are biogeochemical cycles. They're exactly what they sound like. The cycling of various resources or nutrients through biological, geological, and chemical phases, right? And they give us, looking at each one gives us a little bit of a window into how natural systems work and how natural systems can be balanced versus imbalanced. Before we start that discussion, questions from the floor, thoughts? Okay, okay. Um, So we're going to kind of peruse through these, but as we go through them, or the ones that we end up covering, think about what is this resource needed for, and what are its sources and sinks, and what is the human impact, right? So just kind of having this sort of table in your mind can be useful. So, for example, for water, for carbon, for nitrogen, phosphorus, and others. We won't go through all of them, but we're going to use a couple as examples. Okay. Um, in terms of the water cycle, I think many of us are familiar with the water cycle, and we had mentioned it in our discussion so far when we're talking about moisture in soil and moisture and its interaction with trees and the environment. So I'm going to move on to the next cycle, but you can see that cyclical interaction of water through natural ecosystems, and then we know of a lot of the human impacts that alter the temperature of water, water pollution, the filtration of water, so on and so forth. And we will come back to water in our discussion later in the term as well. Okay. The carbon cycle. We talk profusely about carbon when we talk about sustainability. Well, let's talk about the cycle and how it kind of functions, right? So again, thinking about where does carbon exist within, well, first we want to know what is carbon needed for, right? So all life on Earth is called carbon-based life. And if we were to do a little bit of chemistry, we would see that a carbon atom in its valence shell is missing 4 electron interactions. And what that means at like a functional level is carbon is just like a rectangular brick. You can build up, down, side to side because it has 4 connection points. And so living systems are built on that property of carbon, that chemical property of carbon that makes it a building block. And so carbon is stored in all living things. That is one source and sink. Un if those living things die and are fossilized, carbon is in those sources and sinks too, right? So natural gas, fossil fuels, coal, peat, all of that is just ancient dead organisms that have been fossilized in a liquid or solid form, right? And then carbon is also in the atmosphere in what's called an inorganic form, and that's CO2. CO2 is just a gas with one single carbon atom. It doesn't have like this built-up structure that living systems tend to have. But it is the basis of all life because through photosynthesis, it can be incorporated into organic molecules, right? And so when we look at this cycle, we can see the natural balance of carbon is that it has multiple sources and sinks. Living organisms used to be living underground within the soil, and then free inorganic carbon in the atmosphere. Our consumption has led to the exploitation of those used to be living carbon sources and releasing them in an imbalanced way into the atmosphere. That has a number of different impacts. So when we talk about climate change in terms of temperature, CO2 is like a blanket around Earth. It's an insulator and it protects us from UV and things like that. But anytime you use too many blankets, you get too warm, right? And so we're really just layering up the blankets above Earth and around Earth when we're exploiting the carbon that was buried and releasing it. Another thing that happens is ocean acidification. So carbon likes to be in a gaseous form, but it can interact with water. When it does, it makes an acid, right? And so the more carbon you have in the atmosphere, the more acid you have in any bodies of water. And that's why we see things like coral reefs dying off and things like that, and impacts to aquatic systems. Okay? And so thinking about that ecological basis of carbon, where it comes from and where it goes, can be helpful in thinking about the human impact when we utilize various types of carbon sources. Okay? Any questions about carbon or the example of carbon before I go to nitrogen?
Could you repeat briefly how it negatively affects water when it's absorbed?
Yeah. So the
Thank you.
CO2 mixes with water. Water, at its chemical form, is both an acid and a base because its hydrogens can move around. When it interacts with CO2, it predominantly produces an acid, and that's called carbonic acid. And so the more carbon dioxide that dissolves into the water, the more carbonic acid is produced, and it literally just changes the pH of ocean bodies of water. And then that impacts any organism generally. You have organisms that will migrate out of that area if the acid increases, but you have other organisms that are not able to move, sessile organisms. They're particularly impacted because that acid will wear away. Often they have some protective layer, like a shell or something, and that will actually wear away on those protective layers. Um, Kind of similar to how chemicals impact the eggs of various types of birds, and different chemicals, but in this case, it's an acid. And that just impacts oceanic ecosystems across the board. Yeah, thank you for that
Okay.
clarification.
Yeah, thank you.
Other questions? Okay. Um, Nitrogen is another really interesting example. So when you go to the store, when you're gardening, getting ready to garden, right? There's like this NKP, NPK that you look for. Nitrogen and phosphorus particularly, right? And other nutrients as well, are absolutely essential to living organisms and particularly growing plants, which we rely on for food. Remember that we rely on plants for both meat and vegetarian foods because the animals eat plants as well. Okay. Um, and so nitrogen is interesting because it is predominant in our atmosphere. Anyone know what's the percentage of nitrogen in our atmosphere?
Is it like 64 or something? I feel like it's
Even more. Yeah. It's even more. It's between 72 and 78%, right? Yeah, it's amazing. And so oxygen, we just breathe in, right? And then we utilize it. And then carbon dioxide, plants just breathe in and then they utilize it. Well, we're breathing in nitrogen day and night, but because of the chemistry of nitrogen, it is completely and absolutely useless. And this comes down to electrons again, but I'll leave that to a chemistry class. But essentially, nitrogen has three bonds that it wants to make, three electrons that it wants to share, and each nitrogen has three that it wants to share. So they connect up and they share a total of 6 electrons. Now, if you know about covalent bonds in chemistry, just sharing 2 electrons is what makes a molecule. If you're sharing 6 electrons, you have made a very extremely stable bond and connection that is very, very, very difficult to break apart. And the only organisms on Earth that we know of that can do this are bacteria. And so we rely completely in natural systems, caveat natural systems, on bacteria for breaking apart nitrogen, the nitrogen that's in the atmosphere, and releasing it in a biologically active form. And so for historical generations, that's what happened. Now, because nitrogen is so important also to war, during the First and Second World Wars, there's a lot of experimentation with nitrogen, and we were able to artificially figure out how to break that bond. And so artificial nitrogen and phosphorus fertilizers come from that process. And in that way, we kind of tend, or not kind of, or tend, we absolutely overload ecological systems with nitrogen because we have found a cheap way to bypass bacteria. Bacteria are slow. Artificial generation of nitrogen is fast because you put it in a factory, you bombard it with hydrogen atoms at a very high pressure, and you're able to split that molecule. And so what we see, nitrogen is similar to phosphorus, although phosphorus exists in rock instead of in the atmosphere. So you literally have to like mine out mountaintops or mine out, and that's what one of our resources was about this week. And then we overuse it. We overuse nitrogen and we overuse phosphorus on these monocultures that we use to grow soy and corn and whatnot. And it runs out and leaches into various bodies of waters. So just thumbs up or raise your hand if you've ever been to a park and there's a sign that says, don't allow your pets or children into the water because of an algal bloom. Yep. Okay, so that's because we're releasing so much nitrogen and phosphorus into the environment that evolutionarily, that's been like sugar. You know how our bodies crave oils and sugar? Because evolutionarily, they were hard to find. Well, evolutionarily, nitrogen and phosphorus were hard to find. And so any organisms that can take that opportunity and grab it will exploit that ecosystem. And that's what algal blooms are, right? And so thinking about those pressure points and where we have made change versus an image like this, where you have a plant that's making symbiotic interactions with bacteria, which live in these bumps that release nitrogen, that then the plant makes symbiotic relationship with fungi, and that's what these extra mycorrhizae are. And that system that is full and complete, but also slow over time, right? And that those cycling of nutrients. Okay. And so nitrogen and phosphorus being tied to one another in many ways. And we basically had talked about that. Also, nitrogen and phosphorus tend to be in manure. So anytime you separate the utilization of manure for growing crops and then they become runoff, then you get the same eutrophication. And that's what you see here in this algal bloom. There are actually waterways that are permanent, what we call dead zones. So the Gulf of Mexico here has a permanent dead zone because of these are systems, these are networks, right, of waterways that go through lots of lots of farmland and pull a lot of that nitrogen and phosphorus that's in excess into these areas, and you get algal blooms year round. And these are called dead zones, right? So what to do? Well, be part of a cycle, which we already are, right? And so whenever we talk, somebody had mentioned compost when we talked about soil. Whenever we talk about compost, we're talking about reclaiming nutrients and cycling them back into soil systems. And each one of us can do this at their own level or scale. And that's you just basically jumping into the carbon cycle, the nitrogen cycle, the phosphorus cycle in a healthy way. And these small scale gardening projects at schools, in communities, in vacant lots, they are a huge part of reconnecting to these biological cycles and reconnecting folks to those systems in a healthy way. So, questions or thoughts about those examples that we've gone through? Okay, wonderful, wonderful. Um, so I want to move us into our discussion. Why don't we take a 5-minute bio break, and then at 5:40 we'll come back and we'll open up our discussion. Thank you, Yvette, Shay, Matt, and Ivan. Yvette will be our opener, Shay, Matt will be our facilitator, and Ivan will be our note taker. Ivan, I'll shoot you the link to the note-taking file in the chat. Yeah, so go ahead and we'll see each other back at 5:40.